questions about anything from last time? Anything? Well, today's an exciting moment because we're going to consider infinite series, which is a big application of all the things we've been learning, and very important in applications of calculus. Let's see, before I get rolling today, I thought I'd say I told you that one problem, I'd give you some time to think about it, but the page 77, number 12D, was to consider 1 minus 1 over n to the n. And I told you this problem was kind of interesting, and I considered maybe not assigning it. So only thing we know is that 1 plus 1 over n is an increasing sequence bounded above by 3. Okay, that was proved by induction, and I summarized it. I didn't do the details. It's in the book. So it's bounded above by 3, so it converges. Something. And then it converges to, by definition, the famous number e. And e is between 2 and 3. 2.7 something or other. Okay. And I claimed you can do all those problems in number 12 only knowing that. Let's say, assume we know. So, by the way, I'm not grading this problem, so I wanted to give you a time to think about it before I do what I'm about to do here. You can assume, if you want to do this problem, that you know one minus 1 over n to the n converges to a limit L. And of course, all those numbers are positive, so L would have to be greater than or equal to 0, but you can also assume that you know that L is greater than 0. This can be shown similarly to the 1 plus 1 over n to the n fact. But I didn't want you to get that involved in the whole business. But if you assume that, then the whole problem gets more straightforward. Here's the trick. Let's see. Let's write 1 plus 1 over n to the n times 1 minus 1 over n to the n. Let's see, what's that? That would be 1 minus 1 over n squared to the n. And that's 1 minus 1 over n squared to the n squared to the 1 over n. And so if you think about it, as n goes to infinity, we know that this one tends to E, this one tends to L, and what the heck does this one tend to? Well, 1 minus 1 over n squared to the n squared, that's a subsequence of the one that tends to L. So that big question mark is looks like L to the 1 over n. And we know that any positive number to the 1 over n tends to 1. Okay, and I just want to be more scientific about that and show you that. So, 1 minus 1 over n squared to the n squared converges to L because that's a subsequence. And we know subsequences of a convergent series converge to the same thing. So to be, and subsequences of convergent series sequences converge to the same limit. Okay, so that's one fact I'm using. How can I use that fact to deduce the thing I want, namely that looks like L to the 1 over n, and so we would expect it to tend to 1 as n goes to infinity. Any ideas? Well, that thing is a number getting close to L. So eventually it's bigger than something, and eventually it's less than something. And I can squeeze it between those two things. So the moment you realize you can do this scientifically is this: you can use the squeeze theorem. Okay, and so let's think about that. There is an n, natural number, such that, let's see, I'm going to take epsilon to be equal to L over 2. And then I would have L minus L over 2 is L over 2 is less than 1 minus 1 over n squared to the n squared is less than L plus L over 2. That's 3L over 2 when n is bigger than or equal to n. And now I use the squeeze theorem. So L over 2 to the n, or 1 over n rather, would be less than this thing, which is 1 minus 1 over n squared to the n. That would be less than 3L over 2 to the, I'm sorry, to the, yeah, that would be the n, to the 1 over n here. And we know that a positive number to the 1 over n tends to 1. And so the squeeze theorem is going to say that thing in the middle has to do this the same. So the squeeze this goes to 1, 2. Questions about that? That's an important use of the squeeze theorem. You know, the numbers floating around getting close to something, it means that in a limit you can probably treat it like that. But in order to make that scientific, you need to get something a little bit less than it and something a little bit more, and then you don't have to worry about the wiggling around in the middle. It gets squished. Questions about that? Let's see. Oh, last time I defined what it means to go to plus infinity. I figure I'll write out the definition for minus infinity. Last time I defined what it means to say that the limit of a sequence plus infinity. Sometimes we write infinity when we mean plus infinity. And this time I'll define what it means to go to minus infinity. As n goes to infinity of xn equals minus infinity means given, I'll call it script m, given a real number r, no matter how negative, could be a gigantic negative number. I'm adding those words because it helps me understand sort of the feeling for this definition. No matter how negative, there is a natural number, capital N, such that x to the n is less than or equal to this big negative number when n is bigger than or equal to capital N. So I just needed to write that out. So it just means that it eventually gets as big in a negative direction as you want. Let's see, there's some easy facts. Let's see, I'll do an example of a thing that goes to. I told you last time the Fibonacci numbers tend off to plus infinity. But in this typical section of the book, you'd be asked to prove stuff like that from the using the definitions only. So remember, the Fibonacci numbers are first one's 1, second one's 1, then the next ones are gotten by adding the previous 2 together. So that'd be 2, then I add the previous 2, that would be 3, then I'd add the previous 2 and get 5, etc. 8. Dot, dot, dot. Okay, so this would be the first Fibonacci number, the second Fibonacci number, third, fourth. Oh, look at F5 is 5. But then, starting at F6, they're all bigger than, the Fn is going to be bigger than n. So, to actually demonstrate that the Fibonacci numbers go off to infinity, here's how I would suggest doing it. First of all, a simple induction shows that they're all bigger than or equal to 1. All Fn are bigger than or equal to 1. That's easy, because you got the 2 previous ones are bigger than 1, and the next one's bigger than or equal to 1. So no sweat. Easy. And let's see, starting at 6, they're all starting at n equals 6, Fn is strictly bigger than n. Okay, well that's true at n equals 6, so I would use it at induction step. Suppose Fn is bigger than n. Then, of course, Fn plus 1, that would be equal to Fn plus Fn minus 1. And Fn is greater than n. And let's see, so remember we have Fn, this one's greater than n, And this one's at least greater than or equal to 1. So this would be actually strictly greater than n plus 1. And so check. I get the induction step for the n plus first version. Okay. And so, of course, we have the Archimedean principle given an m. The Archimedean principle implies there's an m bigger than that. So it gives me an n with n bigger than m. And so for n bigger than or equal to capital N, I would have, I need n also, I can assume that my n is bigger than or equal to 6. Well, let's see. I'll take bigger than or equal to the max of 6 and n. It's kind of a ridiculous thing to do, but I could have taken my capital N bigger than 6. We have f sub n is bigger than n. Is bigger than, well, capital N is bigger than m. And that's what I want. Well, that's an overkill kind of thing. But that's using only the definitions and basic facts. Questions about that? Let's see. An important, we have some of these famous sequences that are very important to know what they do. So, for example, we know that r to the n goes to 0 as n goes to infinity, when certainly does that if it's 0, but it does it if it's between 0 and 1. And we know other things. We know that c to the 1 over n goes to 0 as n goes to infinity for any positive c. Stuff like that. But today, starting today, another important one is that r to the n goes to infinity, plus infinity, when r is strictly bigger than 1. Of course, when r is equal to 1, it's just 1, 1, 1, 1, 1. So that would tend to 1. Let's see. In freshman calculus, you probably use logs to see that, because you take the. But we don't have logs. So in freshman calculus, you're excited to have logs and exponentials at your fingertips, and you'd write r to the n equals e to the log r to the n equals e to the n log r. And as n goes to infinity, that would go to infinity, because you know that e to the x goes to infinity. And of course, log r is something positive. So this goes to infinity as n goes to infinity, because you learn that about the exponential, and it's because log of r is bigger than 0 when r is bigger than 1. But one of the interesting things about reading the book is that those facts you learned in freshman calculus using exponentials and log functions and integrals, like the integral test, you can deduce them from first principles. And here's how you do it in the case of r to the n. So here's a first principles demonstrations. Which are fascinating and historical also. So let's see. Since r is bigger than 1, so r equals 1 plus something. So b is bigger than 0. Okay, r to the n would be equal to 1 plus b to the n. And there was Bernoulli's inequality, Bernoulli's inequality came from writing out the binomial expansion of that thing and doing an induction. So it was an elementary thing, just following from the binomial expansion. So Bernoulli's says that this is greater than 1 plus n times b. This is Bernoulli's inequality. And let's see, you need to check. This is a valid inequality when b is bigger than minus 1. Check, because b is positive. So Bernoulli's inequality, I guess I should move this down here. Okay, and so now we know that we can make that as big as we want. So this side goes to infinity, plus infinity, as n goes to infinity. I won't do that from the definition, but you know, it's the Archimedean principle again, basically. You can make that as big as you want. So that's how you can see it from first principles. Questions about that? Oh, there's some easy facts that I want you to read about. I don't want to dwell on them in class here. So here's an easy fact. Let's suppose you have an increasing sequence. So we suppose xn is an increasing sequence. And remember, the terminology for an increasing sequence is that those inequalities are less than or equal to. Strictly increasing, they'd be strictly less than. Each term, successive term, would be getting strictly bigger. We know that if it's bounded above, it must converge. Know that if xn is bounded above, then it converges. Let's see if it's bounded above by m. Then we know that the limit as n goes to infinity of xn equals L, and that would be the soup of the xn's. And of course, that would be less than or equal to the upper bound. That's the least upper bound, so that would be less than or equal to any other bound, upper bound. Okay, so if I have an increasing sequence that's not bounded above, then using the definitions, it's straightforward to determine that they wander off to infinity. So today, if xn is not bounded, then the limit is plus infinity. And of course, there's a similar version for decreasing sequences. Similar fact. For decreasing sequences. Except then you have to be bounded below. Okay. This is a particularly important fact about series of positive terms, because those series would give you an increasing sequence. And so a series of increasing terms either converges or it blows off to infinity. I'm going to talk about series starting now. So we've seen some series. So let's see, the series we've seen, I wrote this as a partial sum, S sub capital N, is the geometric series, 1 plus r squared plus dot, 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 plus r to the n. And I played games and showed you how to use algebra to collapse that series, that sum, into a 1 minus r to the n plus 1 over 1 minus r. And then that fact about r to big powers, when r is between 0 and 1, that's going to let us see. So if the SNs converge to L as n goes to infinity, then we say that that sum, we'll write, let's see, we'll write Sn would be a sum as n goes from 0 to capital N of the powers of r. So r to the 0 is 1. And we would write L is the sum from n equals 0 to infinity of r to the n. So that would be the limit of a series. Of course, you've seen these in freshman calculus, and so I'm going to breeze over these definitions. So let's see, now what do we know? We know some facts. Let's do the case. 0 is less than or equal to r is less than 1. And so, let's see, then the S of n is 1 minus r to the n plus 1 over 1 minus r. And that's going to tend to, since the r to the n plus 1 is going to go to 0, that's going to be 1 minus 0 over 1 minus r. And so that sum converges in that case. So the sum from 0 to infinity, r to the n, is this simple thing, 1 over 1 minus r, when r is between 0 and 1. Okay, that's that's one of the most important limits in calculus, and it gets used in complex analysis too. It's very important there. R could be a complex number, that'd be okay. And that same thing would happen if the modulus of r was less than 1. But we're not thinking about complex numbers here. I don't think about that until I teach it at 2:30. Or I'm doing the same stupid thing today. In 425. Let's see. Okay, the r equal 1 case is kind of dumb. Then I'd have 1 plus r, 1 to the 1 plus 1 squared plus etc. plus 1. That would be n times. So that would be equal to, let's see, there's actually n plus 1 of those. So in the case r equal 1, then this would go off to plus infinity as n goes to infinity. And I'm not going to use the formula, although I could use the formula. This r to the n plus 1, that would get gigantic. And so 1 minus that would be something negative in the numerator, going off to minus and getting more and more negative. But the bottom is also negative. 1 minus r, where r is bigger than 1, that's also negative. So that quotient would be positive. And the thing, and because it's getting gigantic in the negative direction on the top, the whole thing would be getting gigantic in the positive direction. So that's one way to think about it. Or, in this case, I'd have here 1, my sum would be, let's see, Sn would be great. This one's great. This one stays the same. But the next one would be strictly greater, because r would be greater than 1. And of course, r squared is even more greater than 1, etc. All those things would be 1. And once again, I would get bigger than n plus 1. So the S of n goes to plus infinity. So let's see. This one would be equal. This one would be strictly greater, etc. So it too goes to plus infinity as n goes to infinity. So to summarize, I would write sum as n goes from 0 to infinity, r to the n equals plus infinity in the rest of the cases when r is bigger than or equal to 1. That takes care of all of them. Let's see. I'm going to do another example here. It's a fun one. Let's take my partial sums, s sub n, to be 1 plus 1 over 1 factorial plus 1 over 2 factorial plus etc. out to 1 over n factorial. That's a very famous series. So that's, and here's why it became a convention to say 0 factorial is 1. Because you were dying to write sum as n goes from 0 to n of 1 over n factorial. So it's just a convention that 0 factorial equals 1. Actually, it makes good sense because you can define factorials for numbers that are not integers. And then when you take the limit as those x factorial, as x goes to 0, it tends to 1. Euler was messing around with ideas like that. And he invented his gamma function. Studied it. So you don't really have much choice in the matter. It's the natural choice for 0 factorial. Well, here's one of those examples. This sequence is an increasing sequence. Because every time I add another positive number. So note, Sn is increasing. Is it bounded above? If it is, then of course this would be a convergent series if it is. Actually, it's a Cauchy sequence, and that's an easy thing to check. Actually, Sn is a Cauchy sequence. So it converges, so it certainly is bounded. Because of that. And that means it's convergent, and that means it's bounded above. Because if it weren't bounded above, it would go off to infinity. Okay, let's see why it's Cauchy. Let's see. Let's check. Usually when you do these Cauchy things, you want one of the numbers to be the big one. And I like to make m be the big one. So let's take m bigger than n. Natural numbers. Then Sm minus Sn, let's see, what would that be? I'd write out those things and I'd write out Sm, and then underneath it I'd write out Sn, and I'd cross out the terms that appear in both. And so what would be left would be 1 over n plus 1 factorial, because I'm killing all the beginning ones out to n. But then I'd have these ones hanging off. So the next one would be 1 over n plus 2 factorial. And I'd go out to 1 over m factorial. N factorials are big, are gigantic, but they're in the denominator here. And so they're so gigantic that I can be really casual about how I estimate them. And so here's the thing to do. Let's write 1 over n factorial equals 1 over 1 times 2 times 3 times 4, etc., times n. Okay. And that is going to be strictly less, well, the 1 over 1 doesn't do anything, but I'm going to leave this 2 there, and this 3 is bigger than 2, and this 4 is bigger than 2. So that's equal to 2. This one's bigger than 2. This one's bigger than 2. And this one's bigger than 2. And so they're in the denominator, so this is less than 1 over 2 times 1 over 2 times dot, 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 1 over 2. How many of those do I have? Not quite n. The first one, number 1 there, is not, I can't use it. It's 1 over 1. So close to n, it's actually n minus 1/2 here. So an easy estimate to check is that 1 over n factorial is strictly less than 1 over 2 to the n minus 1. And so that tail end of the series, I can estimate, and we get S sub capital M minus S sub n is less than, let's see, that would be 1 over 2 to the n plus 1 minus 1 plus 1 over 2 to the n plus 2 minus 1 plus dot, dot, dot. The last one would be 1 over 2 to the m minus 1. And now let's start messing around with that. So let's see, I'll clean it up. That's 1 over 2 to the n plus 1 over 2 to the n minus 1 plus, etc., out to 1 over 2 to the m minus 1. Oh, let's see. I want to make this small, so I'm going to have to play around with it. I'll factor out the first term, 1 over 2 to the n. Then what's left would be 1 plus a half plus blah, blah, blah. And let's see, this would be 1 over 2 to the m plus n minus 1. M is the big one, so that's not, well, it could be 0, but if m was n plus 1, that could be 0. But it's greater than or equal to 0. And I have a formula for this thing. This part is 1 over 1/2 to the m minus n minus 1 plus 1, divided by 1 minus a half. So there's a half in the denominator. I'll put that as a 2 in the numerator and get that this whole thing again is 1 over 2 to the n minus 1 times 1 minus 1/2 to the m minus n. And that's less than 1 over 2 to the n minus 1. 1 minus something is less than 1. 1/2, that 1/2 power thing is between 0 and 1. So it's less than that. And I can make that less than any epsilon I want. So I can make this less than any given epsilon bigger than 0 by taking any big given epsilon bigger than 0. And so it's a Cauchy sequence. Check. That's a famous calculation. Funny, that famous series also converges to E. A fun fact. The sum as n goes from 0 to infinity of 1 over n factorial is another famous series that's equal to E. Questions about that? You can do the same thing if I take a minus 1 to the n factorial. Let's see. N equals 0 to infinity of, if I take a minus 1 to the n, let's see, n, yeah. Equals e to the minus 1. So that's another fun fact. So this sequence is an alternating sequence. Let's see, this would be 1 minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial plus ... And I could use the same estimate to show that those are the Cauchy. I get a Cauchy sequence from those numbers. Because when I did that calculation above, I could have done the triangle inequality and gotten the same calculation. These SNs are Cauchy. By the same calculation as above, because I could take absolute value here, positive terms, the same positive terms. So it'd be the same work. Well, let's see, there's a famous fact. It's called the nth term test. But it'll be the last thing I do today. Famous fact. The nth term test. If a series converges, then the terms have to go to 0. So if those terms don't go to 0, then of course the series does not converge. So it's a one-way test. So it's important to remember this is a one-way test. If the terms do not go to 0 as n goes to infinity, then the series diverges. If the terms do go to 0, you can't claim that the series converges. There's famous examples that I'll get into next time. And another thing to note, if we're only given that the terms go to 0, as n goes to infinity, we can't conclude that the series converges. Can't. So it's a one-way test. And it's a very simple thing to demonstrate. So here's the proof. Let's write, so we have, let's write if I take Sn minus S sub n minus 1, that'd be the sum of the xn's out to n minus the sum of the xn's out to n minus 1. All those would cancel out except the one sticking out of the xn one. So that's equal to xn. And if that series converges, then this would converge to L. This one would also converge to L. So this would be as I'm letting capital N go to infinity. And so we see that the x sub n tends to 0, which is L minus L. So there's nothing to this thing. It's a very elementary fact. Feels like a good place to stop for today. Let's see, in the last 30 seconds here, the famous examples are p-series. And of course, the most important p's that you learned about in freshman calculus, so that'd be the summation of 1 over n to the p, as n goes from, do we take 0? I don't remember. Maybe take n to be 1. Anyway, the sum of the 1 over n's